In the never-ending quest to unravel the mysteries of the universe, the James Webb Space Telescope has emerged as a groundbreaking instrument, revolutionizing our understanding of celestial phenomena. In the year since its launch, this technological marvel has astounded scientists and the public alike with its astonishing discoveries. And now, the premier telescope keeps on delivering on its promises to transform our knowledge of cosmology. It even captured a bunch of subjects so far away that their light takes billions of years to reach it. That's the case with the sensational telescope's latest finds. A massive chain of at least 20 closely packed galaxies from the early universe that could reveal insight into how the most massive structures in the cosmos form. Join us as we dig deep into how James Webb just lifts the veil on the nature of our universe. Back at the start of the universe as we know it, during the earliest stages of the hot Big Bang, everything was brilliantly hot and dense. Not only was the universe filled with quanta of light, photons of terrifyingly high energies, but all the other particles and antiparticles that the laws of physics allowed to come into existence. Given that, energies were tremendous, possibly as high as trillions of times what the Large Hadron Collider at CERN can achieve. Conditions were very dense, causing enormous numbers of high-energy collisions to occur at every instant, and that any particles or sets of particles and antiparticles that could be created would have come into existence as a result of those collisions, so long as they obeyed Einstein's E, mc2. A hot, dense, energetic, primordial soup of particles and antiparticles must have been what existed back then, in the beginning stages of the universe. But this hot, dense universe is also expanding very rapidly, which causes it to cool. The reason is simple. Photons and all massless particles have a wavelength, and even massive particles have a wavelength associated with them, and the size of that wavelength determines the particle's energy. As the universe expands, the stretching of cosmic length scales causes these wavelengths to be stretched as well, to longer and longer values. Longer wavelengths mean lower energies, and so, as the universe expands, it also cools. In the initial stages, practically all of the photons that existed were at extraordinarily high energies, in the gamma-ray portion of the spectrum. But as the universe continues to expand and cool over time, the energy inherent to everything drops. The heavier particles and antiparticles can still annihilate away, but it gets more difficult to create them via E-Teger mc2, since there's less energy in each particle to have a chance of creating them. The unstable particles and antiparticles, as the universe expands and collisions, interactions become less frequent, begin to radioactively decay into lighter, more stable particles. Reactions that couldn't stably occur at higher energies, like protons and neutrons fusing into heavier elements or electrons binding onto atomic nuclei to make neutral atoms, now occur, with the former taking place at a few minutes after the hot Big Bang, and the latter occurring a few 100,000 years after the hot Big Bang. At last, the universe, some 380,000 years after the cosmic story began, is filled with neutral atoms, and the light left over from the Big Bang has cooled down tremendously, to about 3,000 K, with the photons making this bath of radiation up following a blackbody spectrum in their energy distribution. So all of this radiation still exists, and it's luminous. 3,000 K would appear as bright red visible light to human eyes, if there were any humans or human eyes around back then. But the universe is still expanding and cooling. As the universe continues to age, it expands, cools, and gravitates, where those gravitational effects will eventually pull matter into sufficiently large clumps that stars can form. However, that will take time, considerably longer time periods than it takes for the leftover radiation from the Big Bang to continue to cool down past the threshold of being visible to human eyes. Just as heated materials will glow red, but will fail to glow red, if they're below a certain temperature, this black body radiation left over from the Big Bang will cease to be visible after the wavelength has lengthened by a specific amount. As the glow of the Big Bang fades away, the last appreciable amount of photons leave the visible spectrum when the universe is a little more than 3 million years old. About 3.62 million years to be precise. Once it reaches that point, the universe has entered the dark ages. Before any stars form, there will still be reactions inside atoms and between atoms occurring. And while those reactions will produce light, it won't be visible light, but rather radio waves. The biggest culprit here is the humble hydrogen atom, the most common element in the universe. If you were to take every atom that exists in the universe at this time and count it, you would find that about 92% of all of your atoms were plain, normal hydrogen, with a proton for its nucleus and with one electron orbiting it. About 8% of the atoms would be helium-4, a few hundredths of a percent would be helium-3 and deuterium, hydrogen-2, and about 1 atom in a billion would be lithium-7. Nothing else at this early epoch yet exists. But when hydrogen forms containing both a proton and an electron, there's a 50-50 chance that the quantum spins of those particles, the proton and electron, will be aligned or facing in the same orientation as one another, and a 50-50 chance that they'll be anti-aligned or facing in opposite directions from one another. If they happen to form anti-aligned, great, that's the lowest energy state, and no further transition will occur. But if they form aligned, with a half-life of about 9 million years, they'll spontaneously transition to the anti-aligned state, emitting a single photon in the process. That transition, known as the spin-flip transition of hydrogen, will produce a photon of approximately 21 centimeters in wavelength every time. This happens to every proton and electron that spontaneously form a neutral hydrogen atom at any point. 50% of them will form in the spin-aligned state, and then those atoms will eventually all undergo this spin-flip transition, emitting long wavelength photons in the process. However, because these photons are too long in wavelength to fall into the visible light portion of the spectrum, the universe will remain dark. We're going to have to wait until stars form, until clumps of matter in the universe get dense enough to start emitting their own light. First, a little bit via gravitational contraction, and then a lot from nuclear fusion, before there's any way to light up this darkness. According to our best, highest resolution simulations, the very, very first proto-stars ought to begin forming when the universe is between about 50 and 100 million years old, at a redshift between Z30 to 50, where nuclear fusion should ignite in their cores. But, as the very first stars form, the universe still remains dark, as all of those neutral atoms formed back when the universe was just 380,000 years old now serve a second, less desirable purpose. In the dense regions that surround these newly forming stars, they've combined to form molecular gas, and that neutral matter absorbs and blocks the starlight, keeping the universe dark. This is the big problem now. All of those neutral atoms that we formed so long ago are now very effective at absorbing the starlight that's being produced. Even though the first stars should be made exclusively of hydrogen and helium, very high in mass, about 25 times the mass of the average star that forms today, extremely hot, with surface temperatures between 20,000 and 100,000 K, incredibly rich in their production of ionizing ultraviolet radiation, and very short-lived, dying in cataclysmic explosions after only a few million years. There is so much neutral matter compared to the small number of stars that form early on that their radiation cannot penetrate very far. After traveling only a few thousand light-years, at most, it's been entirely absorbed, or, as astronomers say, extincted, by the intervening neutral matter. But there's a little bit of hope here. When ultraviolet photons strike these intervening neutral atoms, The atoms absorbed the light, but at the cost of becoming ionized themselves. In other words, even though there are a tremendous number of neutral atoms in the universe initially, somewhere around a whopping 1080 of them, give or take a few, at this late of a stage in the expanding universe, once you ionize a neutral atom, the electron and the nucleus it was kicked off from are unlikely to recombine, either with the originals or with another nucleus or electron that's been ionized, and form another neutral atom further down the road. This means that all we have to do is wait for enough stars to form in enough regions of space, cumulatively, to emit sufficient amounts of ionizing ultraviolet radiation in order to eliminate these neutral atoms and to turn them into ions, with free electrons and bare atomic nuclei. These atoms, which began as an ionized plasma and only became neutral 380,000 years after the Big Bang, must become reionized in order for the starlight to break free. As a result, we call this process reionization, and it's only when it successfully finishes that we'll state that the Dark Ages have come to an end. Although this process begins when the universe is very young, it is a gradual process that takes a very long time to complete. According to the best measurements we can make, a typical region in space only becomes fully reionized after some 550 million years have passed, but becomes mostly reionized, where 90% or more of the atoms in their vicinity have been converted into ions a couple 100 million years earlier. Some regions will get serendipitously reionized a little bit earlier, while others will take longer than average. Variations can be a few 100 million years, in general. But it's only when all of the neutral, light-blocking matter is gone that we can say, the Dark Ages have come to an end. Although we have simulations to show us how the universe behaves on average, we have to look to the universe itself to actually understand its nature. Luckily, the remarkable power of the James Webb Space Telescope is pushing forward our understanding of the cosmic dawn. In a stunning discovery, James Webb has just discovered a massive chain of at least 20 closely packed galaxies from the early universe, and it could reveal insight into how the most massive structures in the cosmos form. This megastructure, nicknamed the Cosmic Vine in a study published November 8 to the preprint database Archive, swoops through space in a bow shape, estimated to stretch more than 13 million light-years long and about 650,000 light-years wide. For comparison, our Milky Way galaxy is about 100,000 light-years wide. Astronomers detected the vast tendril of gas and galaxies while studying James Webb Space Telescope observations of an area called the Extended Growth Strip, located between the constellations Ursa Major and Boötes. The team was looking specifically for light from very early galaxies, focusing on a property called redshift, a measure of how light increases in wavelength as it travels vast distances through the expanding universe. All of the galaxies observed in the cosmic vine showed a redshift of roughly 344, meaning the light emitted by the objects traveled between 11 billion and 12 billion years, or for most of our 13.8 billion-year-old universe's lifetime before reaching Webb's lens. The cosmic vine is significantly larger than other galaxy groups observed so early in the universe's history, the team wrote, adding it to a growing list of surprisingly huge structures in the early universe discovered by James Webb. According to the researchers, the vine appears to be on its way to becoming a galaxy cluster. These are the most massive structures in the universe bound together by gravity, with masses typically ranging from hundreds of billions to quadrillions of times the mass of the Sun. For now, the cosmic vine has an estimated mass of about 260 billion solar masses and is still growing. But its two largest galaxies may be ready to call it quits. While studying the wavelengths of light emitted by the two galaxies, the researchers found that star formation has all but stopped there, designating them as quiescent or quenched galaxies. The authors pondered, what is the culprit quenching star formation at such an early cosmic time? They noted that it is unusual to find such large galaxies already running low on star-forming gas in the ancient universe. One possibility is that both galaxies are the results of recent galactic mergers, with cosmic collisions triggering wild bursts of star formation that depleted most of the galaxy's available gas about 500 million years before Webb's observations, the researchers wrote. As with many recent James Webb discoveries, the cosmic vine raises more questions about the nature of our universe than it answers, and further study is needed to solve the mysteries locked behind this ancient galactic chain. In a remarkable observation, James Webb gazed back to realms that formed just 2 to 3 billion years after the Big Bang to understand the evolution of several of these early universes. The observations have thrown up some intriguing surprises. Specifically, a Northwestern University-led team of astrophysicists analyzed results from the chemical evolution constrained using ionized lines in interstellar aurorae survey to find that not only do these galaxies appear hotter than expected, but they also seem to host heavy elements, like nickel. The researchers focused on 33 distant galaxies for a continuous 30-hour period. They then combined wavelengths of light collected from 23 of those galaxies to create a composite picture of what's happening in these structures. These spectra contain clues regarding things like their average temperatures and what elements might be lurking within. As Alison Strom, lead author of the study and assistant professor of physics and astronomy at Northwestern University, said in a statement, "This washes out the details of individual galaxies, but gives us a better sense of an average galaxy. It also allows us to see fainter features." The composite picture of the galaxies contained 8 identifiable elements: hydrogen, helium, nitrogen, oxygen, silicon, sulfur, argon, and nickel. While the lighter elements were expected, the presence of nickel, which is heavier than iron in the periodic table, came as somewhat of a surprise. As Strom said, "Never in my wildest dreams did I imagine we would see nickel. Even in older nearby galaxies, nickel rarely is observed. And that's after multiple life cycles of stars, meaning multiple rounds of supernovas, and the opportunity for heavier elements to synthesize and spread throughout the galaxy." Strom believes the higher observed temperatures in these early galaxies might be connected to their curious chemical composition somehow. Ultimately, the fact that we see a higher characteristic temperature is just another manifestation of their different chemical DNA, because the temperature and chemistry of gas in galaxies are intrinsically linked. In another sensational Webb's latest finding, the Supreme Telescope has focused on a region of intense star formation, partially hidden by thick dust, just 300 light-years from the supermassive black hole sitting at the center of our galaxy. This star-forming region, known as Sagittarius C, exhibits 500,000 stars strewn like glitter across a bluish glowing backdrop. One of the major sites owes itself to the James Webb's near-infrared camera and involves members of a dense cluster of baby stars, or protostars, visible just left of center. Within this cluster also lies a burgeoning star that has already assembled a mass 30 times greater than our Sun's, yet is still growing. For this star, it will be a short life. In a few million years' time, the ultramassive object will explode as a supernova, in contrast to stars with masses similar to our Sun's that can survive for billions of years. Stars form inside clumps of cold, dense molecular hydrogen that collapse in on themselves due to gravity. These clumps are laced with interstellar dust that helps keep temperatures within 10 degrees of absolute zero. Absolute zero being the coldest temperature theoretically possible in our universe. In some places, the large, clumpy swaths of dust are so thick that not even Webb's infrared vision can penetrate them. However, we know that deep inside these clouds are nascent stars just beginning to form. Some of those stars, such as the protocluster shown here, have grown to a stage in which their winds can blow away those dusty wombs, rendering the stars themselves visible. The analysis of this new Webb's image of Sagittarius C captured by an international team studying star formation in the galactic center, or Milky Way's heart, is being led by Samuel Crowe, an undergraduate student at the University of Virginia in Charlottesville. "We are seeing lots of features here for the first time," Crowe said in a statement, reflecting on the superior resolution and sensitivity of the 6.5-meter mirror of the largest space telescope ever launched. Among those features are outflows from the protostars that glow like fire when set against the darker, more opaque molecular hydrogen cloud. In front of that dark cloud, to the top of the image, are foreground stars. Around the lower edge are sections of bright, ionized hydrogen energized by the ultraviolet light of other, young, massive stars. This ionized hydrogen had been detected previously, the team says, but the sheer size of the region, 25 light-years across as seen by the James Webb Space Telescope, was a surprise. Crowe intends to investigate this finding further, as well as track down the identity of the needles, or elongated slivers poking radially through the ionized gas in seemingly random directions. Located about 26,000 light-years from us, the galactic center is deliberately targeted by astronomers using the Webb Telescope because it is such an intense region of star formation. Indeed, in some ways, the galactic center shares similarities with early star-forming galaxies James Webb found to have existed just a few 100 million years after the Big Bang. Those galaxies appear brighter than expected. One possibility for why is that they are forming more massive stars than older galaxies are. According to Jonathan Tan, one of Crowe's supervisors at the University of Virginia, the galactic center is the most extreme environment in our Milky Way galaxy, where current theories of star formation can be put to their most rigorous test. In particular, astronomers are probing to see whether massive stars are more likely to form in regions of starbirth at the center of our galaxy than in the suburbs of the Milky Way's spiral arms. Typically, star-forming nebulas give birth to the least massive stars, M dwarfs, and with increasing stellar mass comes a drop in the birth rate. This is illustrated by the fact that there are only a handful of the most massive stars, hundreds of times the mass of our Sun, existing in the Milky Way. This tendency to form more of the least massive stars and fewer of the most massive stars is called the stellar initial mass function, or IMF, and astronomers still do not fully understand what governs it. However, the intensity of star formation in the galactic center may subvert the IMF, leading to the preferential formation of a greater abundance of massive stars. If this proves to be the case, then it may also apply to the earliest galaxies. If they had a higher IMF than we realized, it could explain why they are so luminous, since the most massive stars shine the brightest. As Rubén Fedriani, a team member of Crowe's the Instituto Astrofísica de Andalucía in Spain, concluded in the same press statement, "The galactic center is a crowded, tumultuous place. There are turbulent, magnetized gas clouds that are forming stars, which then impact the surrounding gas with their outflowing winds, jets, and radiation. Webb has provided us with a ton of data on this extreme environment, and we are just starting to dig into it." That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.